Hello everyone, and thanks for watching Edupedia World videos. This is the second video for the topic transverse waves. In the previous video, we finished with the principle of superposition, so let's look at that once again. The principle of superposition basically states that if there are two waves coming simultaneously and reaching a particular point, then the net disturbance due to both the waves will be simply the sum of the disturbance due to each individual wave if the other wave wasn't there. Right. So if the first wave wants to increase the wire displacement of a particle by 20 millimeters, and the second one wants to increase it by 5 millimeters, then when both of them combine together, they will give it a vertical displacement of 25 millimeters. If the second one's tendency was to decrease it by 5 millimeters, then they'll combine and give a vertical displacement of 15 millimeters. Now, this is not always valid. This is only valid for the special case which we have been considering so far, in which the displacements are small, the vertical amplitudes are small. So if the general displacements are small, then the principle of superposition is valid. If a particular wave obeys the superposition principle, then it is called a linear wave, which are the only kinds of waves that are in your syllabus. There are also non-linear waves, which do not obey the principle of superposition. Another important thing which you need to know is that when waves travel from one medium to another, for example, let's say I have two ropes. One is a very thin rope and the other is a very thick rope. If they are both attached together, then the tension at this point has to be equal on the left and right side if this point is at rest. So both of them have to have the same force, but the thicker one will have a greater mu. So the wave velocity will be different in the two mediums. So if I start a wave disturbance here by moving it up and down, the wave disturbance will go like this. It will reach this point and then it will start moving with a smaller velocity because mu will be greater now. So when a wave goes from one medium to another, there is a particular rule which is followed. If a wave enters a region where wave velocity is smaller, then the reflected wave is inverted. Right. So you know this from light, that whenever any wave goes from medium A to medium B, there are some things that can happen. A certain part is transmitted, a certain part is reflected, and for the case of light, a certain part can be absorbed as well. But for the case of wave motion on a rope, it's only reflected and transmitted. So when this wave enters this medium, a certain part will be transmitted, a certain part will be reflected, with the wave velocity going in the backward direction. The net wave in the left direction will be the sum of these two waves going in the right and left direction, and this will be the wave in the right direction. So whenever you're going to a region where wave velocity is smaller, that is where mu is larger, it is thicker, then the reflected wave is inverted. However, if I had my wave going from the thicker rope to the thinner rope, then a certain part would be transmitted and a certain part would be reflected, but the reflected wave would not be inverted as opposed to the original wave. So it is inverted only if it is moving to a region of higher mu. The analog for light waves, which you'll study later on in light waves, would be that if the refractive index is higher, then the reflective wave has a phase difference of 180 degrees, but if the refractive index is lower, then the reflected wave is in the same phase as in the incident wave. Right. So this is another principle which is generally used. Let's start now looking at two particular waves arriving together. So first we'll see two waves traveling in the same direction. So let's say the first wave has a tendency of moving the particles along such that y1 is equal to a1 sine of omega t minus kx. We'll assume omega and k are the same for both of them. Right. Otherwise the net motion would not be periodic. y2 is equal to a2 sine omega t minus kx. So there are two differences between them, the amplitude and there is a phase difference. Actually it might be delta 1 and delta 2, but you can obviously change it such that one of them is 0 and the other is delta. The only thing that is important is the phase difference between the two. So when you add these two, net y, which will be y1 plus y2, will be, you already know this from the case of simple harmonic motion, it will be just like vectors. The net resultant will be a sine of omega t minus kx plus epsilon, where a will be root of a1 square plus a2 squared plus 2 a1 a2 cos theta cos delta. You can try to derive it, it's not that hard. You have to use sine a plus b formula and substitute this from this, and tan epsilon is a2 sine delta by a1 plus a2 cos delta. So this is exactly like vectors, which makes the thing quite easy. Now there are certain special cases. If delta, that is the phase difference between them, is 2n pi, that is an even multiple of n pi, in that case it is called constructive interference. And it's called constructive because then cos of delta will be 1, and in that case you will have a is equal to a1 plus a2. On the other hand, if delta is equal to 2n plus 1 times pi, that is an odd multiple of pi, in that case cos delta will be minus 1 and you will get a will be a mod of a1 minus a2. That is the difference of them, whichever is greater. So you see that the net amplitude has to lie between the difference and the sum of them, and this is called destructive interference. So whenever you're standing in a room and you have two speakers from different directions sending sound to you, they will interfere and cause patterns of constructive and destructive interference. You're not able to tell because generally the wavelength is quite small, so the constructive and destructive interferences are very close together. Now let's look at the more interesting case in which two waves of the opposite direction collide with each other. So we have a rope and one person is moving one end and the other person is moving the other end. This wave is going towards the right, this wave is going towards the left. For simplicity, we'll assume that the phase difference is 0, though you can take a phase difference as well, it won't matter. It will just make the calculation slightly more difficult. So we'll assume that the left one going is y1 and y1 is equal to a, we just take the amplitude to be the same for now, sine of omega t minus kx. What is y2? It will be a sine of omega t plus kx coming in the opposite direction. We'll add them up, we'll get y is equal to y1 plus y2, which if you solve will come out to be 2a cos kx sine omega t. Now this is a very interesting formula. First of all, what it tells us is that the y of any point will be moving in a sinusoidal fashion up and down. And this whole term can sort of be seen as the amplitude. So whenever we have kx is equal to 2n pi, then we'll have the amplitude to be 2a. That is the maximum amplitude. So if this was the a original amplitude, now it will be 2a. Whenever we have kx is equal to 2n plus 1 pi, in that case the amplitude will be minus 2a. So it will be the opposite direction. And whenever we have kx is equal to 2n plus half pi, in that case cos kx will be 0 and the amplitude of the motion will be 0. So we see that there are many points where the amplitude of the motion is 0 and many points where the amplitude of motion is maximum. So what this is called is a standing wave. What we've seen up till now are traveling waves. This particular situation is called a standing wave. And in this particular case, the wave doesn't travel anywhere. It just moves between many situations. For example, initially it might be like this. Then all of a sudden, all particles will start going towards their mean position. Then all of the particles will be at equilibrium together. Then all four particles will start moving away in the other direction. So in standing waves, the phase of all the particles are the same. They're not technically the same. This particular strand or crest has a phase opposite of this, but all of these have the exact same phase. And there are some points which vibrate with a very high amplitude, twice the original amplitude, and there are some points which don't vibrate at all. The points which don't vibrate at all, those points are called the nodes. And the points which vibrate with maximum amplitude are called the antinodes. So you can see this yourself at home if you want to try. If you move these two in opposite directions, then eventually you'll get something like a standing wave, where this will be like this, then it will start moving towards the origin, then it will be flat, then in the other direction, and some points will not appear to move at all. They're actually moving, but at any time their displacement upwards due to y1 will be the opposite of their displacement downwards due to y2, and at every point the net displacement is coming out to be 0. 2a cos x will be what is called the generic amplitude. For any particular point, it changes with x, as we can see. Now, standing waves can be of many types. One of the most interesting one is standing waves with both ends fixed. That means we have two ends that are completely fixed and a standing wave is between them. Let's say like this. Oh, I apologize for the drawing. Let's say like this. So at one point it will be like this, the next point it will be like this. All of the particles reach their amplitudes together, extreme positions together. Then they might all be at the center, and you know what I'm doing. Right. So in this case, what we'll need to have is, so we see that if this was the, original wavelength, now the total length of the string is 3 times the wavelength. It doesn't need to be 3 times, it could also be like this. Right, so it could be 1.5 times as well. But if both the ends are fixed, that means the length has to be an integral multiple of half of the wavelength. Right, because otherwise it will end at some other point and this point will keep moving up and down. The only points that are fixed are half a wavelength apart. So the total length has to be n times half the wavelength for the case of standing waves fixed at one end. Right. From that we can see, since we have the result, I didn't explicitly derive it, but you can, that lambda is equal to v by mu. Lambda is equal to vt basically. So in that case we can write lambda as v by mu, and the result we get is mu is equal to nv by 2l. That can be written as n root of f by mu by 2l. So there are only certain discrete frequencies which can take place if you have both ends fixed. You cannot have a frequency of 21 Hz and a frequency of 22 Hz. If you have a frequency of 21 Hz, then the next frequency has to be a 28 Hz if n was 3 and 4 in that case. So you get the picture. You can only have some discrete frequencies. You cannot have a continuous set of frequencies. Right. So remember this result. We'll come back to this. Mu, I'll just write nv by 2l for now. Right. The second case would be standing waves in which one end is fixed and one end is free. Free means it rotates up and down with the extreme amplitudes. So in that case the situation would be something like this. Right. So this is half a wavelength, half a wavelength, half a wavelength, half a wavelength. And if you want the extreme positions, you're going to have half of that or a quarter wavelength. Right. So in that case, you could just have simply like this, with just one end of this. Right. One end is fixed and the other end is moving up and down. You could have that as well. So it has to be either a quarter lambda or a half n lambda plus a quarter lambda. So it has to be n lambda by 2 plus lambda by 4. Right, n lambda by 2 would fix it like this, which would make a standing wave with both ends fixed. Then you add a lambda by 4, you obviously get one end free. So in this case it will come out to be, this is 2n by 4, 2n plus 1 times lambda by 4. This is L. and we again write lambda as V by mu. So what we get is mu is equal to 2n plus 1 V by 4L. So again we see that for the case of standing waves with one end is fixed, you cannot have any arbitrary frequency. You can have a frequency that is certain multiple plus 1 of a particular value, which is V by 4L. Now I'm going to come to a concept of overtones and harmonics, which generally gives a lot of confusion, especially to students of IIT-JEE, because the naming is slightly not very specific and not very understandable. So we'll deal with two things: overtones and harmonics. And these come up again and again in questions, so we need to know what these are. For both ends fixed, the result we got was mu is equal to NV by 2L. Right? For one end free, we got mu is equal to 2n plus 1 V by 4L. Right? So the different frequencies are characterized in terms of overtones and harmonics, and the naming is important. So first of all, if n is equal to the minimum possible value, in this case 1, in this case it's 0, that means mu being V by 2L in this case, or mu being V by 4L in this case, these are called the fundamentals. I'm talking about overtones now, so let's forget harmonics for now. We'll first talk about overtones. So the basic frequency, the minimum possible frequency, is always called the fundamental. Right? The next possible frequency is called the first overtone. Not the second overtone, the first overtone. The first over the fundamental. So the first overtone for the case of this would be now n is equal to 2. So 2V by 2L. The second overtone would be 3V by 2L. The third overtone would be 4V by 2L. Right? So right now we're talking about fundamentals and overtones. Fundamentals are a subset of overtones. So the basic one is called fundamental. Every possible one higher from that is called an overtone. So in this case, the first overtone will be, try to think of it, n will be 1 now. So it will be 3V by 4L. Second will be, now n is 2. So 5V by 4L. The third will be 7V by 4L. So now, right now nothing is confusing to you because we're just talking about overtones, not harmonics. So this should be clear, I hope. The basic one is always called the fundamental. This is important because often you'll see questions being given such as a string is vibrating with both ends fixed in its third overtone. And you need to know what that means. So that means the frequency is 4V by 2L, not 3V by 2L. Right? That's the place where a lot of students make mistake. And IIT-JEE objective questions love to do these type of things. So the basic one is the fundamental. Everything comes from these two formulas. Remember that. So the basic minimum possible frequency is the fundamental. It is V by 2L for this and V by 4L for this. Every possible frequency after that is called an overtone. So the next possible one is the first overtone, the one after that is the second overtone, the one after that is the third overtone. Next possible one is first overtone, then second overtone, then third overtone. Right? Now let's talk about harmonics, because sometimes a question will not say a string is vibrating in its third overtone. They'll say it is vibrating in its fourth harmonic. So you need to know what a harmonic means. The basic one is always the first harmonic. Right. So the basic one, in this case, this is the first harmonic. Right. Now the way I remember is harmonic sounds like harmony to music, and in music you have to have multiples of notes. Right. So a harmonic is generally the multiple of the basic note. So for example, this is the first harmonic, this is the second harmonic because it's the twice the first harmonic. This is the third harmonic because it is 3 times the first harmonic. This is the fourth harmonic because it is 4 times the first harmonic. Now this is where it starts getting trickier. This is the first overtone, but this is not the second harmonic. This is the third harmonic. Because this is 3 times the fundamental value. It is irrelevant that 2 times the fundamental value is not an acceptable frequency in this case. This is the first harmonic, this is the third harmonic, which is 3 times the first harmonic. This is the fifth harmonic, this is the seventh harmonic. So if one end is free, a string cannot vibrate in its fourth harmonic. Right? I'll repeat this again. First of all, how this will come up in questions. They'll say that you have a string of length 25 meters. The wave velocity is 12 meters per second. You have both ends fixed and the string is vibrating in its third overtone, or the string is vibrating in its fifth harmonic, or the string is vibrating in its fundamental mode. So you need to know what all these are. Right? So I'll repeat again. These are the two formulas from which everything comes. The basic one is always called the fundamental and it is called the first harmonic. The basic one is the fundamental and the first harmonic. Right? After that, if you talk about overtones, you have the fundamental, first overtone, second overtone, third overtone, regardless of what the acceptable values are. So this is the first overtone, this is the second overtone, this is the third overtone. First overtone, second overtone, third overtone. So the third overtone here is actually the seventh harmonic because it is 7 times the first minimum value. Right? So if you have the 25th harmonic, that just means the frequency is 25 times the basic frequency. If it's the 25th overtone, that means there are 24 other possible values between this value and the fundamental value. So they have to do with different things, right? So this is the third harmonic, this is the fifth harmonic, and this is the seventh harmonic. So if a string is vibrating in its seventh harmonic, that means mu is 7V/4L, right? So this sort of sometimes gets confusing because there are two different names, but I hope now it's clear to you and you won't make a mistake in this case. One final topic is left, and that is polarization of waves. Now everything we've seen up till now we'll see again when we come to longitudinal waves, because most things about longitudinal waves are pretty similar. They also add up like vectors, they also have harmonics and fundamentals, and they also can be reflected with both ends fixed or with one end open, and we'll see the exact same things for the case of sound waves specifically and in general for longitudinal waves. So you'll see a lot of similarities, and that chapter will be easier than this. This one property, however, polarization for waves, this exists only for transverse waves. This doesn't exist for longitudinal waves, and that is because the moment you say a wave is longitudinal, you know everything there is to know about the direction of propagation of the wave. We saw this in the beginning of the previous lecture. A to B, if this is the wave velocity is this and it's a longitudinal waves, the particles are displacing in this direction. But if it is a transverse wave and the wave velocity in this, then the only thing we know is that the particles are vibrating in a direction that is perpendicular to this line. Now there are an infinite number of lines perpendicular to this line. You could have this line, you could have the line going in and out of the plane at 45 degrees. You know what I'm saying, right? If you look at it with your eye at this point, then you might see propagation like this, like this, like this. If the rope is coming in and out of the plane, you might choose to vibrate the rope vertically or horizontally or at an angle. And all of these have every property the same, but still are different waves, right? So what is the difference between them? The difference is polarization direction. This direction up and down is called the polarization direction, right? Now everything else could possibly be the same, but these two waves are technically different. Therefore we need a new concept of polarization of waves. We do not need this for longitudinal waves, because if you know the direction of wave velocity, there is only one particular possible direction of displacement of the waves, that is in the direction of the wave velocity, right? So you have many differently types of polarized waves. The way we study polarized waves is that we decompose them into horizontal and vertical. So if the polarization is like this, we can say that it is the equal part sum of the horizontal and vertical polarization. If the polarization is like this, we can say it's more horizontal and vertical. So the way we decompose a vector into its horizontal and vertical components, we can also decompose a polarization into its horizontal and vertical components. So then we'll see that the polarization might be like, the detailed study is not in your course, the detailed mathematical study, but the way it works is y is equal to a1 sine of omega t minus kx, and z is equal to a2 sine of omega t minus kx. Now these a1 and a2 are technically not numbers, they are themselves vectors which have these particular values themselves in angle and magnitude. So the way we can choose to see it is, first of all, going inside is the x direction. So let's say this is the y direction and this is the z direction. If a2 is 0, then it is horizontally polarized. If a1 is 0, then it is vertically polarized. If a1 and a2 are equal, then it is polarized at an angle of 45 degrees. If a1 is root 3 times a2, then it is polarized at an angle of 30 degrees. So the angle of polarization phi is tan inverse of a2 by a1, right, angle with the y-axis. But this actually, now this gets into stuff which is not in your course. It should be mod of a2 by a1, because a2 and a1 themselves are vectors and can have their own phase. So it is actually possible for a1 and a2 to have the same magnitude but a phase difference of 90 degrees. What that means is, when you are at the maximum of z, you are at the mean position of y, and when you are at the mean position of z, you are at the maximum of y. In that case, what happens is what we call circular polarization. And this is seen in light waves very often. And in this case, what happens is, if you're looking at it from inside, the waves go like this. And you can sort of imagine that if you're vibrating up and down, but you keep shifting it, a few seconds later you're vibrating like this, then you're vibrating like this, then you're vibrating like this. So not only will there be a fixed line of polarization, the line of polarization itself will start rotating. So that is called circular polarization, right? This completes transverse waves. We'll start the chapter on longitudinal waves in the next video. Thank you.